At Google, they have created software that improves a step at a time. The editing, the running unit tests, fixing build errors, addressing code reviews, editing some more, fixing more errors, and finally merging the code into a repository. That system is called DIDACT, which is a methodology for training large machine learning models for software development. The novelty of DIDACT is that it uses the process of software development as the source of training data for the model rather than just polished end state of the process, the finished code. By exposing the model to the contexts that developers see as they work, paired with the actions they take in response, the model learns about the dynamics of software development and is more aligned with how developers spend their time. The Google developers here leverage the instrumentation of Google's software development to scale up the quality and the diversity of developer activity data beyond the previous works. The results are extremely promising along two dimensions: the usefulness to the professional software developers and as a potential basis for imbuing machine learning models with general software development skills. And as you can see, DIDACT is a multitasking model trained on developmental activities that include editing, debugging, repair, and code review. And you can see the subtasks there in the various colors, separated in these three pillars: the debugging and repair tasks, the code review tasks, and the code editing tasks. In this effort, they've built and deployed internally 3 DIDACT tools, which are comment resolution, build repair, and tip prediction, each integrated at different stages of the development workflow. All 3 of these tools received enthusiastic feedback from thousands of internal developers. They say they're excited that they have demonstrated how DIDACT is a first step towards a general-purpose developer-assisted agent, and they show that the trained model can be used in a variety of surprising ways via prompting with prefixes of developer activities and by chaining together multiple predictions to roll out longer activity trajectories. And they say they believe that DIDACT paves a promising path towards developing agents that can generally assist across software development process. Now the question is, how was Google able to do this? And the answer is that Google has always had a moat, and this moat is that Google's software engineering toolchains store every operation related to the code as a log of interactions among tools and developers, and have done so for decades. In principle, one could use this record to replay in detail the key episodes in the software engineering video of Google's code base and how it came to be, step by step, one code edit, compilation, comment, variable name, rename, etc. at a time. And this Google code lives in a monorepo, which is a single repository of code for all tools and systems. A software developer typically experiments with code changes in a local copy, which is a copy on write workspace managed by a system called Clients in the Cloud, CITC. When the developer is ready to package a set of code changes together for a specific purpose, for example, say fixing a bug, they create a change list in a system called Critique, which is Google's code review system. As with other types of code review systems, Google developer engages in a dialogue with a peer reviewer about functionality and style. The developer edits the code list to address the review comments as the dialogue progresses. Eventually, the reviewer declares, "Looks good to me, LGTM," and the change list is merged into the repository. In addition to dialogue with the code reviewer, the developer also maintains a dialogue of sorts with a plethora of other software engineering tools such as the compiler, the testing framework, linters, static analyzers, parsers, and other tools. Now let us look at the detail of the multitask model of software engineering that is this DIDACT model. DIDACT utilizes interactions among engineers and tools to power machine learning with things like editing, adding comments, renaming variables, marking up code with errors, and other such tasks. And they have this language which they call dev script that is used to express this formalism. Here you can see a graphic of this DIDACT formalism in action with the specific tasks, their input and their output. They say the DIDACT model is prompted with the task, code snippets, and annotations related to that task, and produces development actions such as edits or comments. These state intent action formalism enables them to capture many different tasks in a general way. What's more, DevScript is a concise way to express complex actions without the need to output the whole state, which is the original code, as it would be after the action takes place. This makes the model more efficient and more interpretable. For example, a rename might touch a file in a dozen places, but a model can predict a single rename action. And the next task they consider is an ML, machine learning peer programmer. And they say DIDACT does a good job on individual assistive tasks. For example, they show DIDACT doing code cleanup after functionality is mostly done. It looks at the code along with some final comments by the code reviewer marked with human in the animation below and predicts edits to address these comments, which are rendered as diff. And you can see it here, given an initial snippet of code and the comments that the code reviewer attached to the snippet, the pre-submit cleanup task of DIDACT produces edits, which are the insertions in reddish color and deletions of text that address those comments. The insertions are in green, the deletions are in reddish color. The human comments are in yellow, which is the reviewer comments. The multimodal nature of DIDACT also gives rise to some surprising capabilities reminiscent of behaviors merging with scale. One such capability is history augmentation, which can be enabled via prompting. Knowing what the developer did recently enables the model to make a better guess about what the developer should do next. That here, which is the history augmented code completion task. And when you add a parameter, the necessary are predicted by the model so as to satisfy that new parameter at some other location inside the code, as you can see here. Such task exemplifying this capability is history augmented code completion. Wow, and look at this today called history augmented code completion, which is also another capacity that comes out of this model. Here below, you can see the developer adds a new function parameter and moves the cursor into the documentation. Conditioned on the history of the developer edits and the cursor position, the model completes the line by correctly predicting the docstring entry for the new parameter. You can see that. That's number 3, the third step. There you go. They say in an even more powerful history augmented task edit prediction, the model can choose where to edit next in a fashion that is historically consistent. If the developer deletes a function parameter, 1, the model can use history to correctly predict an update to the docstring, and 2, that removes the deleted parameter developer without the human developer manually placing the cursor there, and to update a statement in the function 3 in a syntactically and probably semantically correct way. With history, the model can unambiguously decide how to continue the edit video correctly, so that without history, the model wouldn't know whether the missing function parameter is intentional, for example, because the developer was in the process of a long edit to remove it, or accidental, in which case the model should re-add it to fix the problem. So you have this history as context, which makes the correct action unambiguous. The model can go even further. For example, we start with a blank file and ask the model to successfully predict what edits would come next until it had written a full code file. The astonishing part is that the model developed code in a step-by-step way that would seem natural to a developer. It started by first creating a fully working skeleton with imports, flags, and a basic main function. Then it incrementally added new functionality like reading from a file and writing results, and added functionality to filter out some lines based on a user-provided regular expression, which required changes across the file, like adding new flags. So in conclusion, the developers say DIDACT turns Google's software development process into a training demonstration for machine learning developer assistance, and uses those demonstrations to train models that construct code in a step-by-step fashion, interactively with tools and code reviewers. These innovations are already powering tools enjoyed by Google developers every day. The DIDACT approach complements the great strides taken by large language models at Google's and elsewhere towards technologies that ease the toil, improve productivity, and enhances the quality of software engineers. And this is the conclusion here, which is beautiful.